And we are back. Shaler area. This is note video number 15, unit 3, physics, the final note video of science 8. Congratulations, you made it to the end of the year. When you finish this note video, you can start to consider yourselves high schoolers. So the last thing that we need to talk about in the simple machine unit and section is what happens when you start to combine these things together, because that's where modern engineering and modern design and all of that other thing start to play out. Nothing is just a pure simple machine. That's an exaggeration, but you know what I mean. Compound machines are what we use all the time. A car is nothing more than just thousands of simple machines put together. So anytime you have two or more machines together, we call it a compound machine. Something like a wheelbarrow. We've talked about how a wheelbarrow is a second class lever, but it also uses the wheel and axle of the wheel and the axle. Whenever you're tilting it and pouring things out of it, it kind of turns into these other simple machines. So in general, though, what you need to consider when you are building something and whenever you are making a compound machine is that when you have compound machines, you typically have more moving parts. The more moving parts you have, the more friction there will be. So the more compound, the more complicated the compound machine is, it is almost always going to result in a lower level of efficiency than just a pure simple machine. So some compound machines, even things like axes, their levers and their wedges, things like gardening shears are levers and wedges, a couple different levers, a couple different wedges, and we talked about how B. Davis at the high school and I were talking about how the closer you are to the fulcrum when you're cutting, you have a higher mechanical advantage as when you get to the outside. It takes some pretty interesting calculus to kind of figure it all out. Pencil sharpeners, you have your wheel and axle here, because the whole distance around will be the wheel, the axle will be going through the middle. And then you got these wedges in here that are wrapped around cylinders. They're like screws. They shave the wood off. Old-fashioned hand drills are nothing more than just gears, which are wheel and axles. So all of these things are compound machines. Well, how do you figure out the mechanical advantage of a compound machine? It's actually relatively simple. You just take the product of all of the individual simple machine mechanical advantages. Now, do you remember what product is? What math symbol does product? That would be multiplication. So you break your compound machine down into simple machines, calculate the mechanical advantage of each of the individual simple machines, and then multiply them all together. So here we have this simple machine. We have a ramp or an inclined plane. We're trying to pull this thing up. We attach a rope to it. We wrap it around a couple of pulleys. Those are pulleys. We might as well call them pulleys. And then we have a wheel and axle system here. We put another mass on it, and we're pulling down to try to make that go up. So machine number 1 is the inclined plane. It is 4 meters long on the bottom, 3 meters tall on the side. Simple machine number 2 are these two fixed pulleys. And simple machine number 3 is a wheel and axle with a 4-inch wheel and a 3-inch inner axle. What's the mechanical advantage of the entire device as shown? So we have to find the mechanical advantages of each of the 3 simple machine parts. 5 meters divided by 3. Why does that say 5 meters divided by 3 meters? If this says 4 meters and 3 meters, how does that work out? Oh, remember, because you have to remember how all these things work. The mechanical advantage of an inclined plane is the length of the hypotenuse divided by the height. It's the log over the height. So this side of the triangle is 5 meters. How do you figure that out? Well, Pythagorean's theorem. If it's 4 meters on the bottom, 4 squared is 16, plus 3 squared, which is 9. 16 plus 9 is 25. Square root of 25 is 5 meters. So that makes this length of the triangle 5 meters long. It's a 3, 4, 5 perfect triangle. So the mechanical advantage of machine 1, this inclined plane, 5 meters of an incline divided by 3 meters of a height gives us a mechanical advantage of 1.7. Machine number 2 doesn't do anything but change the direction of the force because they're just fixed pulleys, so they just have a mechanical advantage of 1. Machine number 3, if you look at how the rope is attached, this would be the effort force that's running the entire system, and it's applying its effort to the smaller of the wheels of the wheel and axle. So in this case, the input is the small one, and the output is the big one based on how the ropes are drawn there. And that would give you a mechanical advantage of 0.75. So we have 1.7 times 1 times 0.75, and we would get a mechanical advantage of 1.275 for this whole machine. Now imagine if I came in and was like, well, you did that wrong. You built the machine wrong. If you were really trying to get this to work out the right way, you'd probably want the mass to go around the big wheel and the axle to run the rest of the machine. Well, what would that be? How would that change the overall mechanical advantage? Well, is that going to have an impact on the inclined plane? Nope, that's still going to be 1.7. It's not going to change these two things. That's still going to be 1. But instead of it being 3 divided by 4, it would be 4 divided by 3. That would make this 1.3, because it would be 4/3, 1.333. 1.7 times 1.3 times 1 would be roughly somewhere around 2 1/4. So, it's kind of like trying to follow IKEA directions on something where it's all pictures when you're putting things together. Let's say I messed up when I was building this and I put these ropes around the wrong parts. Well, if all I did was flip them, it seems like something very, very minor, right? It's 4 inches and 3 inches. It shouldn't really matter. But if I had them threaded the other way, it would actually like double my amount of force. It would be like adding a whole other Mr. Reagle to help do the job. Little things can have big impacts. Alright, so here's some fun compound machine stuff. This is somebody we've talked about before, Archimedes. They did some Mythbusters things on some of the things here. This cracked me up whenever I was looking for a picture of Archimedes. Somebody made a Pokemon card that is Archimedes, and he's got the Claw of Archimedes attack and the Heat Ray attack, because there is a legend that he devised a bunch of lenses and mirrors to harness the sun's light and turn it into a laser and burn the sails of ships. Mythbusters didn't like it, but there's some pretty interesting speculation and like first-person accounts of him doing these kinds of things. Now, the Archimedean claw, which is what we're going to discuss right now, worked like this if you watch this little video here. Archimedes lived on an island. It was a Greek island, and one of the things that then, if you lived on an island, you had to worry about was being invaded by ships. So Archimedes devised this series of pulleys and levers, and these things were positioned all around the fortresses of the city to literally lift the boats up out of the air and then let them fall back into the water. And when they fell back in the water, they would just get swamped. The water would come up over the outsides, fill it up, and just like sink it to the bottom. They wouldn't have to shoot it or blow them up. All they had to do was lift them up out of the air and take them for a ride and let them drop. Well, how would this work, and what would the mechanical advantage be? So here's a little sketch of all of these things set up, all these Archimedean claws set up around the perimeter of the city, and maybe these boats trying to attack here. So if lever 1, if machine 1 was this lever, and machine 2 was the block and tackle system of pulleys over here, if the lever is 50 feet long over land and 25 feet long over sea, the input side would be the 50-foot side, the output side would be the 25-foot side. That would give the lever part a mechanical advantage of 2. You can kind of see down, oops, I didn't mean to do that. You can kind of see down in these pictures here how the lever was far longer on the city side than it was where it stuck out over the ocean. Now the block and tackle, we can just kind of look and see as it's doing this, I see the other pulley down here. Oh, there, now you can see it. 1, 2, 3. There's 3 ropes in there. So we'll call this a mechanical advantage of 3. Well, 2 times 3. The mechanical advantage of an Archimedean claw is 6. At least as designed and made up here. Typically they would have horses or mules or something that were here that could pull with more force, and then when they lifted that boat up out of the water, there was some kind of a catch pin here that they could just release, and the whole thing would just come crashing back down. So if you needed to lift the boat 20 feet in the air, so you knew that if you dropped it, it would crash the boat. Anything less than 20 feet, I just made that number up, but anything less than 20 feet we'll say wouldn't work. So you have to pull 20 feet you have to make the boat go up 20 feet in the air. Well, how far would the oxen need to pull the rope this way in order for the boat to go up 20 feet in the air? Because remember, you have a wall here. These people can't see what's going on out there. Well, if the mechanical advantage is, we'll just talk about the lever first. If the mechanical advantage is 2, the distance multiplier would be 1/2. If we need to lift the boat 20 feet, which means that would be the output distance, how far would we have to pull down on this side of the lever in order for this side of the lever to go up 20 feet? Well, if the distance multiplier is 1/2, that means we would have to pull this end of the lever down 40 feet before this end went up 20 feet. Well, how much rope would that take? Well, if we needed to pull this down 40 feet and we were using a mechanical advantage pulley system of 3, that means our distance multiplier is 1/3. If in the end we have to move this side 40 feet, that means we would have to pull 120 feet of rope this way in order to actively work the Archimedean claw. Now, in real life, maybe the levers are slightly different. Maybe the block and tackle systems are kind of different. But that's how it would work overall. Alright, check out these pulley systems. They look like they are regular pulley systems, but instead these are compound machines. This is 2 different pulley systems working together. See if you can look at it and figure out what the mechanical advantage of the whole system is. I'll give you a few seconds here to look at it and think. Alright, did you notice that these 2 spots are 2 different block and tackle systems? We have machine 1 over here, and we have machine 2 over here. Well, machine 1 would have a mechanical advantage of 4. 1, 2, 3, 4. Machine 2 is identical to it. 1, 2, 3, 4. So you multiply those 2 together, and this would have a mechanical advantage of 16. What about this one? If I'm pulling here, it's lifting up on this pulley, but when this pulley lifts up, it ends up lifting up on this pulley, which ends up lifting up on that pulley, which ends up lifting our object. There's actually 4 machines here. Each one of these is a separate, simple machine, not really part of a block and tackle system the way that we were talking about it before. So we would multiply each of their mechanical advantages together. So this one, for example, this rope and this rope are holding up the weight or the mass, so mechanical advantage of 2. And the same thing for the rest of them. 1, 2, 1, 2, 1, 2. So 2 times 2 times 2 times 2 is again 16. Alright, gear up for the 15th and final booby trap of physics, as well as the final booby trap of the year. 11 questions. Don't forget to go and fill out the exit slip. This exit slip for this video actually has a couple of survey questions in it that just ask you about how the flipped classroom and the note videos were kind of working for you and whatnot. So I hope everybody learned something. Hope everybody had a great year, discovered something about themselves, and I hope you were challenged. And good luck at the high school.